Welcome to Washington, D.C. in the summertime. And please allow me to introduce myself. For those of you that I've not yet had the pleasure of meeting, I'm Bill Graham, the President's Science Advisor and the Director of his Office of Science and Technology Policy. As you know, this federal conference on the commercial applications of superconductivity extends over today and tomorrow through the end of the afternoon. Today, I'll be serving as the General Chairman for the proceedings, and tomorrow's General Chairman will be the Honorable Donna Fitzpatrick, the Assistant Secretary for Conservation and Renewable Energy at the Department of Energy. And this is Donna Fitzpatrick. Before we get started, I have some housekeeping announcements. First, this entire conference is being videotaped, and in order to maintain the visual and video quality of the taping, I'd like to ask that you not smoke either here in the International Ballroom, at the luncheon sessions in the exhibit hall, or at the workshops in their respective rooms scheduled for tomorrow. Smoking outside these rooms is no problem. Second, the chairman of the workshops are asked to have lunch at a table reserved for them adjacent to the head table in the exhibition center where we'll be holding the lunch. I'm especially pleased to announce that our keynote speaker later this morning will be the President of the United States, Ronald Reagan. President Reagan's initiatives to strengthen U.S. competitiveness in high technology industries was very much the guiding spirit behind this conference. The luncheon address today will be by the U.S. Trade Representative, the Honorable Clayton Yiter, and the speech at the beginning of the afternoon session, different from your schedule, will be by Dr. Dr. Ernest Ambler, rather, the Director of the National Bureau of Standards. This change in schedule was necessitated by an extremely sad occurrence that happened on Saturday. Our speaker had been scheduled to be the Honorable Malcolm Baldrige, the Secretary of Commerce. Mac Baldrige was a great friend and a strong supporter of U.S. competitiveness in the high technology areas. And he too, in carrying out the President's programs, was one of the guiding spirits behind this conference. And in talking to him last week, I know that he was very much looking forward to this conference and to speaking to you. And it's a great tragedy and a great loss that he won't be with us today, but he will be here in spirit. At the head table, we have the Honorable Eric Bloch, the Director of the National Science Foundation, Professor Stacy, Angelica Stacy, Professor Paul Chu, and Professor Robert Schriefler. They will be introduced more fully later in the first session. Last December, a group came into my office to talk about some promising new technologies. And the last one they mentioned was an apparent discovery of superconductivity at 35 degrees Kelvin, nearly twice the temperature at which superconductivity had been observed previously. Remembering the frustrations over the last 25 years in trying to raise the critical temperature of superconductors, I told them to let me know if it was ever confirmed and didn't think much more about it. 2 days later, the same group sent a message that a team at the University of Houston and the University of Alabama had found a material that superconducted at nearly 100 degrees Kelvin. Well, at that point, my skepticism went into high gear, and I nearly threw them out of my office with instructions that said not to come back until there was an independent experimental confirmation of these results. Too often in the past, we've been disappointed with indications of higher temperatures in superconducting. A few days after that, to my very great surprise, one of the most profound discoveries of the 20th century was confirmed. The results of all these discoveries will change the world in ways that we have to stretch our imaginations, even today, to conceive. The discoveries began at the IBM Zurich laboratories, where Dr. Alex Mueller and Dr. John Bednorz first developed a superconductor using ceramics, materials that hardly conduct under normal conditions, and yet superconducted at a temperature much higher than those previously known. Just a few months after this information became available, Professor Paul Chu and his team at the University of Houston and his colleagues at the University of Alabama, under sponsorship of the National Science Foundation and the National Aeronautics and Space Agency, developed a material which superconducted at a temperature of over 90 degrees Kelvin. Most importantly, well above the 77 degrees Kelvin boiling temperature of liquid nitrogen. And let me say a word about what this means. It's not just a temperature difference, but liquid helium costs around $5 a liter, roughly $5 a quart, and it has almost no heat capacity. You look at it and it evaporates. Liquid nitrogen, on the other hand, doesn't boil until 77 degrees Kelvin, but also it costs around 20 cents a liter, much cheaper than liquid helium, and it has something like 60 times the heat capacity, the heat of vaporization, of liquid helium. And so when you put these factors together, you find it's roughly 3,000 times less expensive to cool a material with liquid nitrogen than it is to cool it with liquid helium, not even taking into account the difference in the boiling temperatures. It's very seldom that you find even a factor of 10 in an economic aspect of a technology, and very rare indeed that you find a factor of thousands in it. And that's what we have before us here. It's our good fortune today to have Professor Chu with us for the first session. Earlier this year, in fact, while under continuing support and working with the National Science Foundation, Dr. Chu reported materials that exhibit tantalizing hints of superconductivity at temperatures very close to room temperature, 240 degrees Kelvin. In recent weeks, still others have hinted at similar results at approximately room temperature. And while these materials have yet to be well-established, stabilized, and confirmed, nevertheless, I believe that we have great prospects before us for higher temperature superconductivity, even than the marvelous discoveries we've seen to date. It's a challenge just to keep up with the swift pace of development of these remarkable new materials, and the potential importance of them is enormous. This federal conference on commercial applications of superconductivity, hosted by the Office of Science and Technology Policy and the Department of Energy, is co-sponsored by the Departments of Commerce and Defense, by the National Science Foundation, and the National Research Council of the National Academies of Science and Engineering. This is not a scientific conference, and that should be clearly understood. It is rather a conference about the importance of high-temperature superconductors to American industry and to our economic future in high-technology areas. There have been many scientific conferences on these materials. There will be many more, and we strongly encourage them. But that is not this conference. This is an exciting time, sparked by one of the most important breakthroughs of the century. There's every indication that this discovery will be as significant as the transistor or as the integrated circuit, and will be as pervasive as the use of electricity is in our society today. One example of this is the announcement of the first application of ceramic superconducting materials at liquid nitrogen temperatures, which was made by Dr. James Zimmerman of the National Bureau of Standards in Boulder, Colorado, in May of this year. This device, a superconducting quantum interference device, or SQUID, is used for extremely sensitive detection and measurements of magnetic fields. The device was the result of basic research in enabling technologies in the Electronics Applications Program at the National Bureau of Standards. One important feature of this breakthrough is that it came only 12 weeks after Professor Chu and his team had announced the discovery of the first superconducting material to operate at liquid nitrogen temperatures. In fact, you can see an operating high-temperature superconducting squid in the display areas later today. But this should give you some idea of the compression that's occurring between scientific discovery, experimental and prototypical application, and I think that compression will continue into the industrial and commercial applications of these marvelous materials. We are in a different era from the one we've lived in for the last 40 years. To quote President Reagan in his Quest for Excellence, which was a companion document to his State of the Union address this year, business must work more efficiently, setting high standards of quality, of streamlining operations, discarding outmoded systems and managements, and adapting to change to build on their tradition as entrepreneurs who saw a better way, who had a better idea, and who worked a little harder. That's very much the challenge before us today, and it's important that we here, our home team, get together and talk about how we're going to do that, and that is the purpose of this conference. What the President said in his address has particular significance in today's economy and in our economic environment and in superconductivity applications. We're no longer operating in solely a domestic market. Even at home, we have an international marketplace. Many of our foreign competitors have become keenly aware of their role as global competitors and have marshaled all of their innovative energies in pursuit of U.S. leadership in worldwide markets. And technologically, they are becoming very sophisticated and very able. And I can assure you they'll be working very hard on high-temperature superconductivity, and so must American industry. We have what it takes. America's preeminence in basic research is certainly a strong national asset. In fact, it's unmatched anywhere else in the world. Our 700 federal laboratories, our system of universities, and our countless industrial laboratories together form our national technological enterprise. In addition, the President's determined to provide the environment and the level playing field to support America's global competitiveness. We're moving very strongly, first in government, to keep government from being a detriment to U.S. industry. And second, to forge a strong industry, government, university partnership. This partnership, based on complementary roles for each of these sectors, will continue and increase in support of basic research. Certainly the government role, the federal role of providing a broad base of support in basic sciences will continue and be increasingly strengthened and supported in the years to come. We'll also focus new efforts on high-temperature superconductivity in understanding these materials and in understanding the technologies necessary to enable their use in industrial and commercial applications. Still, the importance of U.S. industry in this enterprise, its initiative, its aggressiveness, its competitiveness, cannot be overstated. If our technology is going to reach the market and pay off for the U.S. economy, you and U.S. industry are going to have to start ahead and are going to have to stay ahead of very tough, determined international competition. Having earlier mentioned the participation of various governmental agencies, let me also say that several professional associations have played a strong and significant role in the formation of this conference, which took place in about a quarter of the time a conference of this size normally requires to call together. It was pulled together in about 3 months with great cooperation from everyone involved. I'm pleased to announce that that cooperation is continuing, and the legacy of this conference will go on to the future. And one example of that is the establishment today of the Council on Superconductivity for American Competitiveness. This council, a nonprofit educational organization, is being dedicated to the advocacy of superconductivity research with specific regard to industrial and commercial enterprises in the United States. My friend, colleague, and predecessor as science advisor to the President, Dr. George Keyworth, will serve as chairman of the Council's Board of Directors. As of today, the Council will be in operation to ensure a continuing high level of interest in superconductivity and in its applications. I'd like to give my best wishes for success to you, Jay, and to the Council. Because we have to make no mistake, we're in this for the long haul, and the Council is one of several major initiatives that will come forward from this meeting and things to follow. This conference has three major objectives. First, the first objective is for American industry to understand what these new high-temperature superconducting materials may bring to a wide range of commercial applications, and what further opportunities are as the critical temperature continues to rise, as I fully expect it will. Second, this conference is for you to hear what has been going on and what will be happening in federally funded research, and particularly at the interface between the basic research enterprise of the federal government and the programs in the universities and in our industrial sector. How to make the great base of research that's provided in this country more accessible and more available to U.S. industry. And the third objective, and from my point of view, one of the most important, is to obtain feedback from you, to hear from you your ideas, your recommendations, your problems. This has to be a partnership, and a partnership has communications in both directions. And that's what we intend to do at this meeting. We're going to have about 1 day of technology, about a half a day of policies and plans, including the President's address, and in fact, with that as the leading statement in our policies and plans, and then 1/2 day in feedback from you. And we look forward to that taking place in the working groups tomorrow afternoon. And those will be arranged in a way that will give you access to a number of different topics. And we're listening hard to your comments. I'm very much looking forward to the results of this meeting, and again, welcome you to it, and thank you very much. I'd now like to introduce the chairman of the first session, the Honorable Eric Bloch. Dr. Bloch has been the director of the National Science Foundation since 1984. Before joining the National Science Foundation, he was vice president for technical personnel development at IBM, one of many major positions he's held at the IBM Corporation since he began his career there as an electrical engineer in 1952. Dr. Bloch is also a recipient of the National Medal of Science and a distinguished contributor to the field of computer design and manufacture. It's my pleasure to introduce Dr. Bloch. Eric.
Thank you very much, Bill, and I appreciate the opportunity to participate in this event, and I want to thank you for taking the initiative for this very important conference. Bill characterized the conference before as half a day of technology and so forth. I want to say that's the first session. It will be 1 hour of science. Recent advances have excited tremendous interest in possible applications, and with good reasons, of superconductive materials. Although the commercial application of superconductivity may be in the future, their significance certainly will be great. But it is well to keep in mind that what has been accomplished so far is largely basic research. We are rapidly learning more about the materials and their characteristics and about the nature of superconductivity itself. A much fuller basic scientific understanding will have to be obtained before we will be able to put superconductivity to widespread practical use. Recognizing the technological importance of superconductivity at temperatures higher than were available only a few short months ago, scientists have long sought new materials that might exhibit higher temperature superconductivity. The recent discoveries by many people around the globe have stimulated the scientific community in an unprecedented manner. Superconductivity is no longer confined to the world of very low temperatures, where cumbersome and expensive refrigeration techniques are required. The National Science Foundation can be justifiably proud of its role in these developments. NSF has been investing for over a decade in this area, and what has been accomplished is a result of basic research, which is a slow, patient process of investigating phenomena without knowing in advance where the search will lead or what the practical results may be. Basic research cannot be planned or directed. It can be encouraged, but it cannot be held to targets or goals. It prospers when the very best men and women are given adequate support and the freedom to follow their own ideas in their own ways. Despite this seeming lack of direction, basic research is the surest road to technological innovation and economic competitiveness. Superconductivity is only the latest major proof of the wisdom of steady support of a wide range of basic scientific investigations and investigators. As our speakers today will make clear, there is a long way to go before we know enough to use superconductivity in economically important technologies. We still have no complete understanding of why the new materials superconduct. We do not know the limits of the new superconductivity, nor do we know how to make materials that both superconduct and also have desirable engineering properties. Much scientific and engineering work will be necessary to fill these gaps in our knowledge, and this conference can contribute greatly to this gap filling. NSF will remain a strong supporter of basic research in this area. In fact, our support has increased greatly over the last few months, both in the scientific, theoretical, and experimental area, as well as in the engineering area of materials processing and materials engineering. But as the work moves beyond basic research, other sources of support will become more important. Industry has already undertaken major efforts, and these will need to grow very rapidly. The national laboratories and government laboratories have a special role, for they can be an important bridge between basic and applied research and between government, industry, and the universities. Our challenge will be to maintain the required level of effort over a long period and to develop cooperative mechanisms that allow universities, governments, and industry to work together. Let me introduce the first speaker this morning. It's Dr. Angelica Stacy, Assistant Professor of Chemistry at the University of California in Berkeley. She's also, I might want to add, one of 1,000 faculties that have received the NSF's Presidential Young Investigator Award, a 5-year award totaling a maximum of $500,000, which includes industrial support. I'm proud to say that she has full industrial support, but as she said before, she can use more. She received her PhD from Cornell in 1981, and her achievements in the synthesis of superconducting materials place her at the forefront of research. Dr. Stacy.
Well, I'm very happy to have the opportunity to tell you about the status of chemistry, of the chemistry of these new materials. May I have the first slide, please? Do I have? Okay. Well, as you all know, superconducting transition temperatures were stuck at 23 Kelvin for many years. In fact, the field of superconductivity was asleep, you might say, and most scientists and engineers were very pessimistic for new technologies employing superconductors due to the expense of liquid helium. And I think we also believed that we would never get to much higher temperatures. But then, as you all know, Bednortz and Mueller came out with a claim that there was a superconductor above 30 Kelvin. They actually knew of this work, I think it's interesting to note, in January of '86. It was published in October, and it wasn't until December that many of us believed or that this was really a true result. I think that really shows where we felt the field of superconductivity was. There had been many other claims of high-temperature superconductors that had never been substantiated. And then usually the first claim is the most important one, but very quickly thereafter, Chu and his co-workers discovered the yttrium-barium copper oxide that superconducted at 90 Kelvin. Well, since that time, many things have happened. Even though we're not very good at predicting things, we're very good at understanding these materials. I think we know a lot about their structures, a lot about the chemistry and physics in a very, very short period of time. I might add that there are some amusing things that have happened. In addition, there are new journals of physics. I think you all are now reading the New York Times as the journal of physics. The People's Daily of China is also very popular. As a chemist, I think it's important that I reach a much larger audience. And I think it's appropriate that the next time you're standing in line at the supermarket that you look at the National Enquirer, because that's where I'm sending my work now. You can just imagine the title, Alien Spaceship Powered by Molten Superconductor. Anyway, let's go on, and I'd like to tell you about the synthesis and characterization and our understanding of the chemistry. Here's a picture of the structure of the yttrium-barium copper oxide. Now, the lanthanum-strontium copper oxide is nothing unusual. It's a material that it has a structure that many minerals have. It's nothing out of the ordinary. But the structure of this yttrium-barium copper oxide really took us by surprise. We didn't expect to see this packing arrangement for the atoms. Shown on this picture, I don't want to go into too many of the details, but the copper atoms, I've lost the, oh well. The copper atoms are shown in black, and the oxygen atoms are the open circles. And I think what's apparent to everyone sitting there is that the yttrium atoms, which are the hash circles, are separating sandwiches. And I think most of you can see that this material is made up of sandwiches where the bread is the copper-oxygen layers, and in between copper-oxygen layers, the meat, so to speak, are chains of copper and oxygen, and the whole material is held together by, if you want to refer to them as the olives, the barium atoms are in between the bread. Now, the most important point or feature of this structure, which is going to cause us problems, there are two of them. One is that the oxygen atoms have more sites that they can occupy. There are a lot of vacancies in this structure, and it turns out that we can easily move out some of the oxygens. And when we pull those oxygens out, the material no longer superconducts. So we need to be very careful about getting the oxygen stoichiometry right, and we don't understand everything we need to know yet about how the oxygen atoms have to be placed in this structure for the best properties above liquid nitrogen temperature. I think the other thing that's very apparent is that this material is anisotropic. It has preferred direction to it. In fact, we know there's good evidence that the conductivity is preferentially in the sandwich and not perpendicular to the sandwich, and it makes us worry that for applications we may need to order these sandwiches to get the best properties, and that could cause some problems in processing. Well, let me have the next slide, which tells you something about how to prepare these materials. Now, to prepare powders of the material, what you need to do is get the elements, the metals, yttrium, barium, and copper, well mixed. Now, the best way to do that has been referred to as the Julia Childs approach, and that's simply to take the oxides of the metals and grind them together. Some people are using coffee grinders to grind the material. You can use microwave ovens, apparently, to heat the material. But this approach has some drawbacks. We don't want to sit around for hours and hours grinding this material together. So we'd like to find other ways of mixing the powders. And the way that that's been done to go to less grinding is we'd like to get these metal oxides into much smaller particle size. And a way we've tried is to use techniques that have been used for other ceramics. Now, it turns out that those techniques work, while they work well for most ceramics, have some drawbacks for the superconductors in that they leave impurities behind. I've listed those techniques as in 2 and 3 as precipitation routes to making metal oxide powders. They're fine for ceramics. They don't work for these superconductors because of the impurities which are left behind. Now, we don't want these impurities for one very important reason. We have superconducting grains. If we have impurities which separate the superconducting grains, we're going to have very low critical currents. And for most applications, we really need to have high currents that carrying capability for the superconductor. Ultimately, the chemists need to work on methods to get to, so that we don't have to grind at all, so that we can get the elements mixed atomically. On the next slide, I have listed some of the particular aspects of the way you need to heat these powders once you've mixed them. And to begin with, we find out that we need to mix this we need to heat these powders at 750 centigrade to get the superconducting phase to form. If we heat much lower than that, we don't form the superconductor. Now, this is a real surprise because most oxides can be formed at much lower temperatures, and it also causes us problems because if we let the material react at lower temperatures, we form more impurity phases. So we need to find ways of getting the material quickly to high temperature where we form just the superconducting phase. In the second case is what I've already mentioned. We need to get these powders as homogeneous as possible before we begin to react them. If we don't, we form impurities, and a really bad impurity is a low temperature eutectic which forms. Now, what this means is that barium and copper alloy, and they form a liquid phase which coats all the superconducting grains. Again, this drastically reduces the critical current, and we need to find ways to avoid forming this material. The sintering temperature has to be below 970 centigrade. If we go above that, the material decomposes, and so we have a very limited range in which we can form these materials. The fourth point that I want to make is something that we don't like to hear when we think about applications, is that these materials are not very stable in air. They react with water, they react with CO2, and we need to find ways to protect them from the atmosphere. We don't know all the variables involved yet as far as the reactivity with air and water goes. All right, and then finally, I want to say that the samples need to be annealed once they're formed. So this is, although I said they're formed at 750 centigrade, they actually lose oxygen at 750 and don't form a phase which superconducts. So if you just react this material at 750, you have a material which doesn't superconduct. You need to cool it then and let it pick up the oxygen necessary to superconduct. All right, on the next slide, just quickly, I want to show that we can use the state-of-the-art tools like electron micrographs, electron microscopes to show how well ordered this material is. But then on the following slide, those are images of the atoms in the material. On the next slide, we can see that there are lots of defects, particularly near the surface. There are amorphous regions. I think most of you can see that there's well-ordered material, and then towards the surface, there's a lot of defects that we need to learn to get rid of. On the next slide, I just want to mention that we've learned how to grow single crystals. IBM and Bell Labs have grown some very large crystals, which are important for understanding the properties of these materials. Thin films, IBM has done some very spectacular work in making epitaxial films. And then on the next slide, I just want to list here, there are only 2 new classes of superconductors. We hope to find more. We have clues from the ones that we know, which are the lanthanum strontium copper oxide and the yttrium barium copper oxide. We have clues for finding new materials, and we have a lot of hope that we'll be able to get to new classes of materials. And then let me just conclude by saying on the last slide that the most important points that I'd like to get across are that these materials are highly oxidized. They lose oxygen. We need to learn how to keep them oxidized and in the superconducting state. When they lose oxygen, they don't superconduct anymore. They're near metal insulator transition. All I mean by that is that the that the insulating form doesn't superconduct, the metallic form does. It gives us also a clue as to where to look for new materials. They have a very limited range of stability, and we have to worry about the fact that we have superconducting grains which are coated by impurities, and we need to get rid of these impurities. Well, let me just leave you with the fact that whenever we have a new material, we really have great hopes for new technologies using these materials. Thank you.
Thanks a lot, Dr. Stacy, for a very fine talk and for starting us off on the right level. Our second speaker this morning is Dr. Paul Ju. He's, of course, known to you all as a scientist principally responsible for the breakthrough which led to this conference. Bill Graham mentioned that already before. Dr. Ju is professor of physics at the University of Houston and has been supported by the National Science Foundation for 14 years of patient work preceding this year's dramatic progress. My only question is, what took you so long, Paul? He also recently completed a tour as an NSF rotating program officer, for which we are very thankful. He will tell you of the continuing search for superconductivity at still higher temperatures. Dr. Chu.
First, I would like to thank our chairman for giving me this opportunity to describe the current experimental status of high-temperature superconductivity research. Could I have the first slide, please? And I think, oh, the other side, please. The right-hand side slide, please. The next slide, please. The next slide, please. I think in today's presentation will be made in the following order. First is brief introduction and the knowns and unknowns of high-temperature superconductivity, and a brief review on the prospects of superconductivity at temperature much higher than 100 degrees Kelvin, and finally a few concluding remarks. Next slide, please. I think we all know today is the continuation of yesterday. What makes it possible for us to be here today to discuss the potential commercial application of high-temperature superconductivity is due to the broad-based and sound knowledge accumulated over the last several decades by many in different fields like physics, chemistry, material science, and engineering. And I would like to recognize the following. I think the field of high-temperature superconductivity was formally inaugurated by Ben Mathias, John Hume, and Ted Jabor for their steady and persistent work on A15 intermetallic compound alloys, which were made finally superconducting at temperature around 23 degrees Kelvin by John Gavella of Westinghouse and Lou Testardi of AT&T Bell Labs back in 1973. And unusual superconductivity in oxides can be traced back to the pioneering work by Schooley, Holster, and Cohen on reduced strontium titanate back in 1964, and then by Al Swidler and Ben Mathias on sodium tungsten bronzes back in 1965, and lithium titanium oxide by Dave Johnston and co-worker in 1973, and then the barium lead bismuth oxide by Art Slade of DuPont and his co-worker back in 1975. Barium lead bismuth oxide is particularly unusual because of its unusually high transition temperature, what we call the TC, at around 13 degrees Kelvin, in spite of its small electronic density of states and the absence of transition metal elements. It is this very compounds which had captured our imaginations by our group at the University of Houston and Alabama in superconducting oxides in our long and tedious search for superconductivity at even higher temperature ever since its discovery more than about 10 years ago. And I think the drastic advancement in TC were not made until last year by the reports of superconductivity at 35 degrees Kelvin by Badnautz and Miller. And then later on, superconductivity above 90 degrees in yttrium barium compound, copper compounds by Wu, Ashbourne, Thorne at Alabama, Huntsville, and Hall and his colleague, including myself, at the University of Houston. And I think several weeks later, several compounds were found superconducting above 90 degrees, and this finally, we therefore enter a new era of high-temperature superconductivity, which we may call the modern era of high-temperature superconductivity. Let me have the next slide, please. I would like to briefly describe what we know and what we don't know about high-temperature superconductivity above 90 degrees. What we have known is that the transition temperature is between 90 and 100 degrees Kelvin, and the current density for the sinter material is around 10 to the 3rd ampere per centimeter square obtained by AT&T Bell Lab and others. And also for thin film, it goes all the way up to 10 to the 21st ampere per centimeter square obtained by different laboratories, including IBM, Stanford. And the carrier concentration of this material is quite low. It's approximately 10 to the 21st. It's about 100 times lower than ordinary superconductors. And the maximum magnetic field this class of material can stand is around 200 Tesla, which is the highest yet obtained by any, so far by any people. And the universal gap equation concerning the energy gap of this material has been obtained between 1.2 to 20, so the value depending on the method of determination and the samples. But it was also obtained from specific measurement based on the prediction. The specific heat jump is approximately 1.43 gamma times Tc, and that number was obtained by the Berkeley group. And we also observed some glassy behavior in this material. Could I have the next slide on the other side? The next slide, please. And the next slide, please. As you can see here, the magnetization jumps as we cool the temperature down. It behaves like a glassy state. And the structure of this material, as Dr. Stacy already shown, shows some layer structure. And the superconductivity, based on our experimental data now, we know that superconductivity should be remain confined mainly to the 3 copper-oxygen layer region. And we know the coexistence of superconductivity and antiferromagnetism in this class of material. And from the experimental data, we also know the electron form pairs in this class of material, and substantial fraction of the electrons are participating in superconductivity of this material. And partial isotope effect has been observed in the class of material, shows superconductivity around 30 degrees, and no isotope effect has been observed in the superconductors with 90 degrees superconducting transition temperature. And we also know that the superconducting material can be made into semiconducting material and also can be made into magnetic material without changing the chemical elements. Could I have the next slide on the right-hand side, please? I think here are the summary of some of the unknowns concerning the superconducting pairing mechanisms. There are many models have been proposed, but none of the experiments so far could unambiguously identify the superconducting mechanisms. And the second question is about the dimensionality of superconductivity happening in this class of material, whether it's 1 in the linear chain or 2 just in one single layers, or 3-dimensional, meaning that all these layers are coupled somehow to a certain extent. And we also don't know too much about exactly about the valence states of copper. All these models depend so heavily on whether the copper forms 2 valence states or 1 or 3 valence states. It's not clear at the moment. And then we also don't know exactly the implications of the isotope or partial isotope effects of, in this material. And the glassy behavior of this material, whether it's intrinsically associated with the structure of the material or extrinsically associated with the processing of this material, because this can become very important in our future application of the material. And of course, As I mentioned, that we found coexistence of magnetism and superconductivity in this class of material, but whether this occurrence are accidental or one is the consequence of another remains unknown. And we also know that superconductivity is happening in this class of material, which can made from metallic state to insulating state. This simultaneously appearance of these two phenomena in this class of material, accidental or again is a consequential one of the other, remains unknown. And the roles of oxygen and defects has been found to be extremely important for superconductivity, but whether this affects superconductivity through the change of a stoichiometry or the symmetry or the linear chain is unknown. And the stability of this material through thermocycling and interaction with its environment or the electric field effect or strain and stress effect, again, is unknown. So now let me go on to the next slide, please. I think many people are very interested in knowing what is the current status of possible superconductivity at substantially higher temperature than 100 degrees Kelvin. I think in the past, to establish the existence of a superconducting state, we have two criteria to meet. One is the zero resistivity, and the other is Meissner effect in a large fraction of the material. But for this new class of material, I would like to add two more criteria. One is the stability, and the third is stability, and the fourth is the reproducibility. By stability, what I mean is that the material can survive thermocycling long enough so careful diagnosis can be carried out to make sure that whether it's superconducting or not. By high reproducibility means that we can predict when the sample is going to become superconducting before we made it, and also we would like to see that not just one laboratory can see the phenomena, but all laboratories all over the world can make the samples, even though with the probability less than 100%, but at least it's predictable. In order to satisfy all these criteria, I think right now the highest temperature remains between 90 to 100 degrees Kelvin. If we're going to relax some of these criteria, for example, if we accept zero resistivity and partial Meissner effect, then I think the highest TC now one can think about is 225 degrees Kelvin. If we relax the criteria even further, just accepting zero resistivity, then the highest transition temperature is around 290 degrees as announced by the Berkeley group several weeks ago. If we relax all these rules, just taking the sudden drop of resistivity as an indication of superconductivity, then the highest TC would be around 360 degrees Kelvin. Could I have the next slide, please? The next, please. So with all this, we believe that the first element is not crucial to superconductivity, and I think if those unusual things really represent real superconductivity, it must occur in some grain boundary conditions. In order to overcome some of this problem, we try to control the uncontrollable. And right now what we're doing is through evacuation, we found that we can enhance the temperature by more than 10 degrees. And also we use electrical field effect. We can raise the transition temperature by more than 10 degrees. Also now we are trying to fine-tuning the synthesis conditions in the hope of raising the temperature higher. I believe concerning the stability and reproducibility problems, if we can overcome one, the problem will be settled. Whether we can really get the material stabilized at that high temperature for application right now remains unknown. Could I have the next slide, please? Oh, I'm sorry, that's the slide. I think there will be a lot of promise and challenges lying ahead in science and also in possible high temperature superconductivity substantially higher than 100 degrees Kelvin. And I think also in the area of applications, and I believe there exists large promise in the novel applications which have not been conceived, and we have to spend more effort along that line so the novel applications can be made to, and tailored to the new unusual superconducting characteristics of this wonderful class of material. And I have been particularly thrilled by the strong support and enthusiasm from the scientific community, funding agencies, and also most of the important of all, the general public. But at the same time, I hope that all this support should be steady and will not be made at the expense of other areas of science. And I think a long-sustaining and broad-based science research program will be very important to maintain the U.S. competitiveness in the world. Thank you.